Welcome to today's lessons on motor load calculations. We're going to spend a good deal of time in the code book today. If you haven't got a code book already, I would suggest having one for this. I'm going to put up the relevant tables in this PowerPoint for those of you that don't have them. But if you have your code book, it is good habit to start practicing flipping between these tables, and that's one of the things we want to learn when we're taking these classes is how to navigate the code book. And so if you have your code book available, then by all means, instead of looking at the tables on the screen, pull yours out and start practicing flipping to these sections of the code as we talk about them. Today's lesson objectives: to find the full load current of different sizes and voltages of motors using the tables 430.247, 430.248, and 430.250. Those are the tables that deal with the full load current or full load amperage of different horsepower motors. We're going to properly size the overload protection for individual motors. We're going to calculate the wire size for branch and feeder conductors supplying those motor loads, and we're going to properly size the overcurrent protection, the breakers, for branch and feeder circuits that supply these motor loads. We've got a few definitions we want to go over before we start with today's lesson. Overcurrent device, you may see it as an OC device, is a device designated to protect a service, a feeder, branch circuits, equipment such as motors from excess current by interrupting the flow of current. So a few examples of these, right? So the breaker, if we have an overcurrent, the breaker is going to trip, or the fuse is going to blow. Also in this category are motor heaters, which we'll get into a little bit more when we go further into this. But that's an overload device specifically for the motor that is typically adjustable for a specific situation for each particular motor. Full load amperage, you may see abbreviation of FLA along with the next one, the full load current, FLC. The full load amperage, FLA, represents the amount of current a specific motor is designed to draw at a rated horsepower. And this is the number that will be printed on a motor on the nameplate. It is what a specific motor has been tested at and what it is designed to run at by its specifications. Full load current, it represents the amount of current that has been calculated for a generic motor at a rated horsepower. So if we know that we have a certain horsepower motor that's going to be put into a location, when we're deciding what size circuit, what size wires we're going to pull to that motor, we don't know if that particular motor may get replaced at some point in the future. So we want to bring wires that are big enough for any motor that's at that particular horsepower that's put at that location. Whereas when we're choosing the heater size, when we're choosing the protection for the specific motor, we're going to want to know the amperage of that specific motor. And so they look similar. We'll make sure we try to keep these separated. I'll do my best to keep them separated as we talk about them. Full load amperage is the nameplate amperage. Full load current is the code book amperage. And then an overload. That's a condition in which equipment is being operated in excess of its normal full load rating, or the conductor in excess of its rated ampacity. In either of these cases, if we allow that condition to persist, it will cause damage. An overload of amperage will create heat that will if it persists, will cause damage or a dangerous overheating situation for a motor or set of wires. As I mentioned a moment ago, Article 430 covers motors, motor circuits, and motor controllers. If we're looking at doing the calculations for what size of everything that we need, right? We have to start at the end. We have to know what all motors are going to be on this circuit. And once we know what all motors we need, uh, we're able to start going through this 6-step process of finding the amperage of each individual motor. And we have to find the amperage for each individual motor so that we can work back to the beginning. We have to know, we have to figure out based off of the amperage of those motors what wire size we're going to select. We're going to need to, based off the specific amperage of each of those motors, know what size thermal overloads to protect each of those motors. We're going to need to know, that we're going to use those amperages to decide our branch circuit protection, and then our feeder conductor size and our feeder overcurrent. And this is it's a 6-step process that we're going to go through to get from all of the motors all the way back to our main circuit breaker for the entire system. And we'll work through those one at a time. I do have a little worksheet that I've included in your Blackboard that you'll be able to, that you should, if you can, print off and look at it. I will hand that out when we come to class on Thursday. If you're wanting to familiarize yourself with it, you may want to take a look at it before then. Our first step in finding what size wires, what size breakers we need for a motor is we need to know what the current of that motor draw is. And so when we look to do this, we're going to look in the tables listed in 430.248 through .24250. We're going to look at those tables depending on what kind of motor it is to pull that amperage from. Each of these motors should be stamped with a nameplate that has the amperage that it draws on it, but we're not allowed to use that for most of our calculations. Most of our calculations are going to need the full load current, the FLC, which comes from the code book. So the first step is finding the full load current. We need to know which of these tables are we going to draw from. 247 is for DC motors. 248 is for single phase motors, and 250 is for 3-phase motors. There are a few others, .249, a couple of others that are for motor types that are more rarely used. The most common two are going to be the 248 and the 250, the single phase and the 3-phase motors. So just to work a few examples here, the first step would be finding out, okay, we have a 3-phase motor, and if I have a 3-phase motor, I'm going to need to be looking at table 430.250. That is our 3-phase alternating current table. So the next thing I'm going to be looking at, right, is the voltage in the motor. It's a 230 volt motor. So I'm going to scroll across here till I find 230 volts. 3 horsepower. I'm going to scroll down till I find 3 horsepower. And then if I look where those two meet, I'm going to see that we have 9.6 amps. Our second 3-phase motor, 480 volts. All right, we see right here it says 460. It doesn't say 480, it says 460. But if we look up here in the top of it here, it says that voltage listed are rated motor voltages. The currents listed shall work for 110 to 220, 220 to 240, and 440 to 480. So it's listed at 460, but if we have 480, we can use this 460 volt column, and we're going to go down to a 50 horsepower motor. I'm going to look at where those two run together, and I'm going to get a 65 amps. That 3 horsepower, that was 9.6 amps. 208, right? If I have a column for 208 here, going down to the 1.5 horsepower, where those meet, I can see that I have 6.6 amps. Now, my next motor is a single phase motor, so I'm gonna look at the table 430.248, which is my single phase chart. I can see the first one is 240 volts. Same here, right? I have 230. I'm allowed between 220 and 240. So if I have this one says it's 230. We were at 230, so we're good there. 3 horsepower. I go down to 3 horsepower. I'm sorry. Single. I'm looking at my wrong row. Single phase, 240, 3 horsepower. 240 will work for my 230 column, will work for 240. 3 horsepower. I look at where those run into each other. It is 17 amps. I look at my next one, single phase, 120 volts. The 115, it will work for 120. 5 horsepower. That's 56 amps. Right? We can look at when you look at the difference of voltage and the difference between single and 3 phase. Up here I have a 50 horsepower motor that is only drawing 65 amps. Right here I have a 5 horsepower motor at 120 volts that is drawing almost the same amperage, drawing 56 amps. So by changing the voltage and moving from single phase to 3 phase, we can do a lot in reducing the amount of amperage that a device draws, that a machine needs for its power. Then lastly, we have 208 volts, which will be this column right here. 1 horsepower motor, so that is going to be 8.8 amps. Can you guys see how we're getting these things out of these tables? We find the correct table for either single phase or 3 phase, and then we find the column for the voltage, we find the row for the horsepower, and then where those meet, that is the full load current. Each of these listed would be our full load current. It's right there in the title of both of these tables, full load current. That's step 1. Now we move on to step 2, which is wire size. And so to choose our wire size, we're going to take the full load current from the last step, right? We've found our full load current in amps for each of these. And then if it is a continuous duty motor, we're going to multiply it by that full load current by 125%. Now, how do we know if it's a continuous duty motor? Well, any motor that runs more than 3 hours is going to be a continuous duty motor. So for a commercial application, basically all motors are continuous duty. If it's not continuous duty, there are some side steps that we can take in 430.22 in A through G that will make us some allowances. The most common type in the commercial environment is going to be the continuous duty. Those are going to be the ones that we focus on today. So when we choose a wire size, right, we're going to have to choose that wire size from the 60-degree column if it's an ampacity of less than 100 amps, and the 75-degree column if it's used if we have more than 100 amps. I'll show you how that works a little bit more in just a moment. So we're going to work right back through the same problems that we were just working on, right? This is the way that it, generally you're going to be working from a motor from one end all the way to the other. So this first few steps, we'll look at the same thing at each of the steps. We've got our three-phase 230 volt 3 horsepower motor with in our last section on step 1, we calculated that the full load current was 9.6 amps. So if I want to know what size wire I need, if it's a continuous duty motor, then I have to up that 9.6 amps slightly, because it may draw more than 9.6 amps, or because it's running continuously. Amperage is a thing that as it's running through the wire, it creates heat. And if a motor is running continuously, there's nowhere for that. If there's nowhere for that heat to dissipate, then it can cause damage over time, even if we are at the chosen amp size. So we're going to up the size of the wire slightly if it's a continuous duty motor that's going to be running constantly and causing a situation where we can't bleed off that extra heat. So if we've got our 9.6 amps and we multiply that by 125%, we're going to get 12 amps. So if we get 12 amps, what size wire do I need? Well, I guess it would depend on what kind of wire we're using. Let's say you're using THHN, right, which is this wire right here. Let's try that again with a highlighter instead of try that again with the highlighter so that you can see it. THHN. So if we're using THHN, 12 amps, well, that ought to be a size 18 wire. We're not allowed to use this 90-degree column. Even if we're using THHN wire, when we're choosing our wire size, we are limited to the 60-degree column and the 75-degree column. If the amperage that we're working with is less than 100 amps, then we can use the 60 amp column, and if it is over 100 amps, then we can use the 75-degree column. And the reason for this is, although we're choosing a wire size based on the insulation and its other properties, we don't know what the terminations for that wire are going to be hooked to. We don't know, is the device that it's hooked to rated for 90 degrees, or is it rated for 75 degrees, or is it rated for 60 degrees? We have to work on the assumption that it may not be. And so if it's less than 100 amps, we use the 60-degree column. Now, if it's more than 100 amps, those devices are required to have at least 75-degree terminals, and so we can use the 75-degree column, because anything that's over 100 amps, all the terminations have to be able to handle the 75-degree conditions. So when looking at our 12 amps from our first problem here, we've got 12 amps. I can see that 14 AUG will hold 15 amps. Now, I don't have anything listed above that on either of these two columns. And the reason for that is, if you notice 14, 12, and 10, all three have little stars, and each of those little stars says that we can put a maximum of 15 amps on a 14, 20 amps on a 12, and 30 amps on a 10. Regardless of the wire type, regardless of the temperature ratings, if it's a 14, 12, or 10, we can only put 15 amps on the 14, 20 amps on the 12, and 30 amps on the 10. And for the purposes of hooking up motors or hooking up anything in a commercial building, We're not allowed to use a 16 or an 18 for any of those connections. A 14 is the smallest connection that we can use. Okay, so let's take a look at let's do another example here. We've got the 3-phase 480 50 horsepower motor. We calculated that at 65 amps. So if it's at 65 amps, we're going to use once again our 60-degree column, and then we're going to multiply that 60. First we have to find our continuous duty, right? 65 amps times 1.25, 125%, gives me 81.25 amps. So if I have 81.25 amps, I'm going to go down in this column until I get a wire size that is big enough to hold at least 81 amps. That's going to be a 3-AUG wire is the smallest wire size that will hold at least 81.25 amps. We have to go up. We can't choose a wire size that is smaller. Let's take a look at another one. So we're looking at, we have a 3-phase 208 volt. Now, if you'll notice, nowhere in this table does it say anything about voltage. We're choosing the ampacity here, and for ampacity, when we're looking at ampacity, the wire size doesn't care what the voltage is. It cares what the ampacity is. The ampacity is what creates the heat, right? If we change the voltage, that can change the amperage that's being drawn by something, but it's the amperage that draws the heat. So our limiting factor is amperage. So if we have a 208 volt 1.5 horsepower motor with a full load current of 6.6 amps, we take that 6.6, if it's continuous duty, times 1.25 to get 8.25, and there would probably be that number 16 would probably hold 10 to 12 amps. It would hold enough amps, but we're not allowed to use it. That 14 is the smallest wire size that we can use. Looking at the next problem, the single phase 240 3 horsepower motor. The only thing we need to know out of that whole list is the 17 amps. If it's continuous duty, 17 amps is going to be 21.25 amps once it's padded. And so when we look here, our number 12 is only good for 20 amps. So we're going to have to go up to the number 10 size wire. Next, we have a 120 volt 5 horsepower motor with a full load current of 56 amps. Where is that going to fall? Somebody want to, I don't guess any of you guys can talk to me on here, so I'm going into teacher mode asking you guys questions. Take a look for just a moment and see, pause the video, see if you can figure out 56 amps times your 1.25 or 125%. What wire size is that going to be? 56 amps times 125% is going to be 70 amps. That's going to be a number 4 wire, 4-AUG wire. And then lastly, for our table here, we have a 208 volt 1 horsepower 8.8 amps. Once we pad that at 125%, you can get 11 amps, which is going to come in at a 14 AUG. Working as another example here, right? If we're wanting to find the conductors to a single motor, we have a 1 horsepower 115 volt single phase motor. It says the motor has 75-degree terminals. If we look up here at our chart, first step 1 is find our full load current. So it's a 1 horsepower 115 volts. That's going to be 16 amps. Then for our wire size, we're going to multiply that 16 amps times 125%, right? This is a sump pump. You know, I might argue about whether or not a sump pump is going to run 3 hours continuously, but you know, in this situation, we're considering that it does. So we're going to multiply that by 1.25 or 125% to get 20 amps. And so if it's 20 amps, what size wire do we need? So we're going to go to table 31016. If you've got your book, flip to 31016. Practice doing that. We're going to find the 60-degree column that's good for 20 amps. That's going to be in number 12. A couple more examples just to practice doing this, right? If we got a 40 horsepower, 3-phase wound rotor motor at 208 volts, our first step is going to be table 430.250. We're going to look for the full load current for that 208 volts, 40 horsepower. Comes at it, the full load current is 114 full load current amps. If it's continuous duty, we're assuming that it's continuous duty because this is a commercial environment. Almost all motors in a commercial environment are. We're going to multiply by 125% to get 142.5. Next step, to choose our wire size, we're going to table 31016. We're looking for, we're over 100 amps, right? We're at 142 amps, so we get to come into the second column here this time. This is our 75-degree column. We use a 75-degree column when we're talking about things over 100 amps. So if we need 142, that's bigger than a 1 alt or a 1 AUG, and we're going to be in the 1 alt size. The 1/0 gives us 150 amps. That's the size that we're going to need for that particular motor. One more, 150 horsepower DC motor, 240 volts. So for this, we're going to need table 430.247, where we can look and see that a 150 horsepower, this very bottom one here, we're looking right at the bottom, 150 horsepower, 240 volts. It's going to be 506 full load current amps. Take that 506 full load current amps times 125%. We're going to get 632.5 amps. All right, pause these videos, work these problems as we go, so that you can practice. Right? Now we're going to look at 310.16. We are well over 100 amps, so we get to use that second column. Using the 75-degree column, and we're going to need 632 amps. It's off the chart here. Oh, here we go. Let's pull this other chart up where we have a little better view of it. So 75-degree column is our 75-degree column. Scrolling all the way down till we get to 625, 650. So that's going to be a 1750 copper wire. Right? Now, when we're dealing with motors, we're going to be using copper. There is a second part of this chart, this aluminum wire. If we were choosing something for, say, pulling lighting or something that was some type of load like that, this is a non-inductive load. We could use the aluminum in those situations. Generally, for an inductive load such as a motor, we're going to be using copper. All right, our first two steps, we've talked about our full load current. We've talked about the wire size for the branch circuits going to each specific motor. Next, we're going to talk about the separate overload device, the specific overload device that is specifically for each motor. These are many times called the overload heaters. For this is only place where we use the nameplate amperage if it's given. If for some reason the nameplate's been ripped off, you can't read the nameplate amperage, then we can use the full load current then and work from there. So when we pull this amperage off of the device, we're gonna use 430.32A is our minimum, right? So if a motor is marked with a service factor of 115 or greater, then we're gonna take that full load amperage times 125%. If that motor is marked with a temperature rise of 40 degrees Celsius or less, we're going to multiply it by 125%, one or the other, not both, right? We're not doing it twice. If it's got one of those markings, either one of those markings, it's 125% of the full load amperage. And then any other motor, we're going to take that full load amperage and multiply it by 115%. And then that number, whatever that number is, let's say we have a motor with an amperage of 16 amps marked with a temperature of 44 degrees Celsius. So that's going to be less than this one. We weren't given a service factor, so we assume that it's an all other motor. 16 times 115% equals 18.4 amps. Now, is there a size 18.4 fuse? Probably not. We are going to use the next size up fuse, or if we're using a thermal type overload that's built into a motor starter, those are typically adjustable, so we're going to choose the size that the minimum is as close to 18.4 as possible, so that we have some range to go up if it's necessary. Because the part 2 of this says that when the setting or sizing of the overload device selected is not sufficient for the motor to start, right? If it trips when we start up, then the higher setting or size of overload may be employed, as long as it doesn't exceed 140% for motors marked with the service factor of 1.5 or a temp rise of less than 40 degrees, and then 130% for all other motors, right? So we're supposed to check first at the lower one, and then if the motor trips, then we can increase it up to one of these larger ones. And with a integral motor starter with heaters, generally we have a little bit of adjustment there where we can adjust to dial in so that the motor has enough time to get started up. That's what these are giving us the opportunity for. When we're using slow blow fuses, or we're using heaters that have a delayed reaction, because when we start up a motor, there is a very high inrush current. A 20 amp motor, if it's drawing 20 amps when that motor is running, if we start that motor from a dead stop with a load attached to it, that motor may draw 60 or 70 amps for a split second, or for up to a second. As the motor comes up to speed, it may be drawing a much larger amperage than what the motor rating says that it is rated for. And so the wire can handle that for a very short period of time. We need a fuse or a breaker or a heater that for a very short period of time can handle that inrush so that it doesn't trip. And so if it's a situation where with our overload, our thermal overloads for the device that it does trip, we can get one that is marked for up to 140% if it has that service factor, or if it's less than 40 degrees Celsius, and then up to 130% for all other motors. This is our maximum. So let's just look at this. Let's look at this same little problem here. 16 amps marked with a temp of 44 degrees Celsius at 130%. That's going to be 20.8 amps. I think it was at around 18 amps. So we're going to be between 18 amps and 20.8 amps That's going to be our range that we can use. We want to use the lower one if possible, but if it fails, then we can go up to 20.8. This is just a picture of one of those adjustable overload relays. It's a three-phase relay. We have line 1, line 2, and line 3 come in the top. Line 1, line 2, and line 3 come out the bottom. Right? When this contactor gets the signal, it pulls in to allow electricity to flow from line 1 out T1, from line 2 out T2, and from line 3 out T3. And it flows through the adjustable overload heaters. And if you see right here, there's a little set screw. We can adjust the amperage on these, and you can buy these in different sizes so that for the specific motor and specific situation that you're using, you're going to dial in that amperage so that the motor doesn't trip on startup and that it runs smoothly during operation. All right, just to work a couple of practice problems here where we're practicing pulling this information off of the nameplate. We got a three-phase motor with a nameplate 7.8 amps at 230 volts with a service factor of 1.15. Now, once I get to this step in the process, I should have already calculated my full load current from the code book. I'm not using it to choose my heater size, right? When I'm looking to choose my heater size, I'm going to take that 7.8 amps that's on my nameplate. Because I have a service factor of 1.15, I use the 125% to give me 9.75 amp minimum overload size. And if it fails to start at that minimum size, I can multiply it by 140 to bring me up to 10.92 amps, right? That is my minimum and my maximum. It has to, those overloads have to be somewhere in that range. So, well, now we can move on to step 4, our branch circuit overcurrent protection. And this is going to be a spot where if you've been doing residential, if you've been doing commercial, if you've just been like wiring things up, it's going to freak you out a little bit, right? Because when we talk about a 20 amp receptacle or a circuit with 15 or 20 amps on it, we're using number 12 wire, that's good for 20 amps. We're putting a 20 amp breaker on that wire, right? We're limited to using a 20 amp breaker on that wire. That is not the case for motors, right? When we talk about motors, because of that high inrush current, especially if like at the home panel, if we just have an instantaneous trip breaker, you could have an inrush current, on a 20 amp motor that's going to be 60 or 70 amps. We're going to want to make sure that that breaker isn't going to trip every time you start the conveyor line, right? We're going to need a breaker that's big enough not to do so. Now there are several different choices to choose from when we're looking at those. Step 4, we're going to be using table 430.52, and so it has a couple of columns there where you've got a time delay fuse, a non-time delay fuse, an instantaneous trip, and an inverse time breaker. Now, depending on the situation that you're in, you may have a different one, right? If I put a motor, right, that is a 20 amp motor, let's go back to say we got our motor that's drawing 18 or 20 amps, and I am putting that on a 60 amp breaker. That inrush current, that spike of inrush current at 60 amps is not going to trip that breaker. But that overcurrent device that's closer to the motor, it's going to protect the wire. It's going to protect the system from something that's close to the same size as the motor, right? That was set at 125 to 140% of that device's potential, of that motor's potential overcurrent, that's what's going to trip if we get a small overload, right? If we get a dead short, right? If somewhere in this system I have two wires that just come in contact with one another, that is going to create basically infinite amperage immediately, and so that is still going to trip this this breaker, even if it is set at 800% of the amperage that motor is drawing. If we get a dead short, it's going to instantaneously trip. That is a huge amount over 800%. It's going to trip immediately, and so we're still protected, even though it feels a little bit wrong to be putting that large of a breaker. I just know that like it is in the code book. This is the way that this will be done, right? So we're going to go to table 430.52. We're going to pick the type of protection device that we're using, whether it be instantaneous trip or inverse time breakers or some type of fuse. We're going to take the full load current that we found earlier, and we're going to just multiply that by the percent in the chart, whatever percent it is for that particular kind of breaker. So for example, we'll go back to our last little example there, 16 amp full load current using an instantaneous trip breaker. So if we're using the instantaneous trip breaker, we're going to multiply that 16 amps times 800%. We're going to have a breaker that is at least 120 amps. There's not a 120 amp breaker, so we got to round up to the next size. We're actually going to be using a 150 amp breaker for a 16 amp load. And I know that sounds weird and that feels weird, but that's what happens with an instantaneous trip. With an instantaneous trip, that inrush spike, there is no delay in it tripping the breaker. And so we need, if there are other options available if you know you're going to be running motor loads, you may want to use inverse time breakers. So for example, that same 16 amp load, we're going to use an inverse time breaker. And so we only have to multiply that by 250%. And that's going to equal 40 amps, which still is a good bit more than 16 amps, but it feels a whole lot better than putting in a 150 amp breaker for a single 16 amp load. Now, when we're looking to find breaker sizes, right, when we do these multiplications, a lot of times they don't come out even. You come out with 128 amps. There's not a 128 amp breaker. There is a table in the NEC, table 240.7, which lists the standard size fuses and breakers that are required to be made in the different sizes. Step 5 is feeder conductor size. This is going to be found in the code book 430.24. And when we're dealing with feeder conductor size, we're going to be talking about the wire that is going from our main panel at the beginning of the building that is feeding to our sub panels where each of our motors drops, right? So we have our 3 phases that are feeding each of these motors. And so, step 5 it's what it tells us is we're going to take the largest motor, whatever the biggest motor is. In this example here, there's 2 motors, and one is drawing 40 amps, the other is full load current is 28 amps. We're going to take that larger one, we're going to pad that one by 125%, right, just like we've been doing, and we get 50 amps there. And then we're going to add the full load current of all the other motors, and I covered it up there, but our other motor is 28 amps, so we get 50 amps plus 28 amps gives us a total of 78 amps. So when I'm looking for what wire to use, right? It's less than 100 amps, so I'm using the 60-degree column. If it is less than 100 amps, we use the 60-degree column. And I'm scrolling down. I got 70 and then 85. So the number 3 has an ampacity of 85 amps. So that's going to be the wire that we choose there. All right, last step. Step number 6, our feeder overcurrent protection. Here we're going to take our largest branch circuit protection and we're going to add the full load currents of all the others to it. All right, so what that means is, right, we're going to find our biggest motor, right? This was our biggest motor, and we're going to take our branch circuit protection, the 70 amps. So this one has a 70 amp branch circuit, and then our smaller motor, it has a 35 amp branch circuit, but we're not worried about its branch circuit protection. We're worried about the second motor, or second and third, or second and third and fourth, however many additionals there are. We're going to add just the current, so the full load current, to the device. So that's going to give us 84 amps, the 70 amp branch circuit, and our 14 amp full load current gives us 84 amps. Now this is the one spot in all of this where we're going to round down instead of round up. Why are we going to round down instead of round up? Well, we're assuming that we're not going to be starting all of these motors up at the exact same time, right? We've padded all of these devices and motors and breakers have been padded for us to start them for an extra inrush startup current. And so we're going to be at least assuming that we're not going to be starting every motor at the same time, and so those inrush currents are going to be staggered, and so that we should be able to round down here to the next size breaker, once again using that 240.7, which will give us the next breaker size down from 84 amps is a 80 amp. So that's the last of this week's lesson on motor load calculations. Make sure that you guys are checking your Blackboard, keeping up to date with when you've got exams, when we're going to have changes of classes, when things, there's a lot going on in the summertime. Keep an eye on your Blackboard so that you know the latest of what exactly is going on campus and in this class. On Blackboard right now, there is the 6 steps that we went through. There's a handout that'll walk you step through step on that. It'll come in handy for your exam that's coming up. Make sure you're prepared for that you're watching Blackboard for notifications on when that exam is going to be and how to take that. That 6-step handout will help you out a lot with that. Make sure you're coming to class. We're going to go over all of this lesson. We're gonna rehash that in class, and you guys will be able to ask questions, places where you're having sticking points. We'll go through several example problems, practice, just giving you 3 or 4 different motors and have you work that all the way back through to the end for class, and hopefully that'll help some of you guys out and get you guys ready for your test after that. So if you got any questions, you can email me or see me in class this coming week.